Hey everyone, and welcome back. We're diving into some pretty intense physics today. Gluons.
Yeah, always a fascinating topic.
You guys sent in some really cool stuff, an article that lays it all out, and then, wow, some abstracts from some pretty hardcore science papers.
Definitely going deep on this one.
So, where do we even begin? I guess the article tries to sum it up by calling gluons the, quote, cosmic glue. So, like holding quarks together.
Right, to make those protons and neutrons. And those are, well, kind of important for, everything around us.
Makes sense. But the article also says the force these gluons carry, the strong force, it gets like stronger the further apart things are.
Exactly. It's pretty unique that way, unlike the other forces. The strong force, the more you try to separate those quarks.
The harder it pulls them back together. It seems kind of backwards.
It does, yeah. Think of like a rubber band. The more you stretch it.
The stronger it snaps back.
Okay.
Okay, I get that. And that's what keeps quarks trapped inside bigger particles.
Exactly. That's color confinement. No free quarks roaming around.
Color confinement. Cool name. So, gluons, they're like the prison wardens of the quantum world, huh? And the article mentioned they're massless and moving at the speed of light.
Yep. Pretty amazing when you think about it. All that power, but no mass. And to describe all this crazy behavior, we have quantum chromodynamics. QCD for short.
QCD. Okay, getting a little complex now. But the article mentioned something called asymptotic freedom that comes from QCD. What's that all about?
Basically, it's super high energies, like think back to the Big Bang.
Okay, way back.
The quarks, they almost act like they're not even bound together, free to move around as they please.
So more energy, less bound. That's kind of weird.
It is counterintuitive, but that's the quantum world for you. And it's key to understanding how matter behaved in the early universe. Scientists can study that quark-gluon plasma.
Whoa, quark-gluon plasma. Sounds intense.
It was there just after the Big Bang, giving us clues about how everything evolved.
So gluons, not just holding stuff together, but a window into, like, the origin of everything.
Wow. Right. And maybe clues to dark matter, even unifying the fundamental forces. Big stuff.
Lots to think about. But before we go too far, the article mentioned glue balls. Sounds kind of sci-fi. So gluons are the glue, but can they stick to each other?
Theoretically, yes. Glue balls, particles made entirely of gluons.
Okay, so, like, did those actually exist, or is this just a theory?
That's the thing. Super hard to detect. No conclusive evidence yet, but the hunt is on.
Exciting. So how are scientists even tackling this?
Lots of ways. One is this technique called lattice QCD.
Lost me there a bit.
Like imagine space as this tiny grid 3D chessboard almost. And at each point, you simulate how those quarks and gluons interact.
So like supercomputer stuff.
Totally. Simulating a whole virtual universe.
So it's like a physics video game almost.
In a way, yeah. And they use it to try and find those glue balls.
Pretty wild. So how do we even figure all this out in the first place? About gluons, I mean.
Long journey. But back in the 70s, particle accelerators, you know those giant atom smashers?
I've heard of them.
That's how they saw gluons, confirmed their role.
By smashing stuff together, we can see these tiny things. That's amazing.
Right. And today, the Large Hadron Collider, the LHC, it's a key tool for this.
Ah, the LHC. So still smashing stuff to study gluons.
Absolutely. Looking for things called gluon jets.
Okay, gluon jets. Tell me more.
So when high-energy gluons are made in those collisions, they break apart, produce streams of other particles we can see.
So it's like we're studying the aftermath, the debris, to understand the gluons.
You got it. Like figuring out how a clock works after you drop it and it breaks.
I like that analogy. So smashing things, looking at the pieces, trying to work backwards to those gluons. Pretty cool.
It is. And understanding them, it's not just for, curiosity's sake.
Oh. I mean, that's enough for me, but what else?
It impacts all sorts of fields, from how the universe began to potentially solving our energy problems.
Wow. Okay, gluons, you're way more important than I first thought. But it feels like we've only scratched the surface here. What else are scientists trying to figure out about them?
Well, there's a lot. Gluons can interact with themselves. That opens up a whole new can of worms.
Okay, self-interacting gluons. I'm intrigued.
Remember those glue balls? That's just one consequence. There could be a whole hidden world of gluey interactions out
A
there.
hidden world. Sounds like we're heading into some serious uncharted territory. And speaking of uncharted territory, those scientific papers you mentioned, they seem to be diving even deeper. Okay, let's see what these papers have to say. What kind of insights are they giving us?
They really highlight the complexity of gluon dynamics.
More complex than what we've already talked about. I'm
Yeah.
not sure my brain can handle it.
I know, right? but fascinating nonetheless. One paper delves deeper into that asymptotic freedom we talked about, but in a much more mathematical way. They even use the analogy of gluons acting like springs.
Hold on, springs. We've had glue, rubber bands. Now springs. Are we building a physics-themed Rube Goldberg machine here?
Eh, maybe. But it shows how hard it is to really grasp these concepts. They defy our everyday intuition. That's why those advanced computational techniques are so vital.
Like that lattice QCD thing.
Exactly. One paper goes deep into how they use it to simulate quark and gluon interactions, understanding things like color confinement and searching for glue balls.
So we're using computer simulations to explore the quantum world. That's pretty mind-blowing. And what about the other paper?
That one mentions something really interesting, applying machine learning to study gluons.
Wait, machine learning? Like the stuff they use for, like, personalized ads and facial recognition?
Yep, that's the one. Seems strange, but it's super powerful for analyzing the massive data from experiments like the LHC.
So we're using algorithms that, like, learn from cat videos to try and understand the strong force. That's wild.
It is, but those gluon interactions are so complex we need all the help we can get.
True enough. So we've got these powerful theoretical tools, giant experiments, and now even AI, all focused on these tiny particles. But why? Why are they so important?
Well, fundamentally, it's about understanding the very fabric of our universe, right? One of the fundamental forces holding matter together. But there's more to it than that.
Okay, I'm all ears. What else can gluons tell us?
Think about it. They could be the key to unlocking nuclear fusion, clean energy. If we can really grasp this strong force.
We could potentially, like, harness the power of the sun.
Exactly. Not just about abstract physics anymore, huh? This research could have a real impact on all of our lives.
Definitely raises the stakes. And we talked about dark matter and the early universe. What else can gluons teach us about the cosmos?
Well, studying them at high energies, we get glimpses into those first moments after the Big Bang.
So we're using these tiny particles to look back in time, billions of years.
Pretty much. Like a microscope for the early universe. Helps us understand how it all evolved.
Incredible. From cosmic glue to the origins of the universe. It's a lot to take in.
It is. But that's the beauty of science, isn't it? Always more to discover, always more to learn.
Well said. We've talked about what gluons are, how they behave, the experiments, the implications, but I feel like there's still so much more to uncover, right?
Oh, absolutely. The world of gluons is full of unanswered questions and exciting avenues to explore. It's a field that's constantly pushing the boundaries of what we know.
So where do we go from here? What are some of the big unknowns scientists are still wrestling with when it comes to gluons?
One of the most fascinating areas is the search for exotic particles. We touched on glue balls, but there could be even stranger things out there.
Like what? Give me an example.
Well, we've got these building blocks, quarks and gluons, interacting through the strong force. We know they form protons and neutrons, maybe glue balls. But could there be other combos, other kinds of particles we haven't even imagined yet? Like there's this idea of hybrids, particles with both quarks and gluons bound together.
So it's not just understanding gluons themselves, but all the different ways they can, like, team up to potentially create whole new forms of matter.
Exactly. Like, you know those Lego sets? You can build the instructions, but then you can get creative and combine those bricks in ways no one's thought of before.
A cosmic Lego set. Instead of castles, we're building the universe. Okay, I gotta ask, if we did find these exotic gluon particles, what could they tell us? Could they, like, rewrite the physics textbooks?
It's hard to say for sure, but they could definitely give us clues to some of the biggest mysteries out there.
Like what?
Well, for one, maybe dark matter.
Dark matter. You mean that stuff that makes up most of the universe, but we can't even see it?
The one and only. We know it's there, but what it's made of, no idea. Some theories think it might be particles interacting through forces similar to the strong force, maybe involving gluons or these exotic gluon particles.
So we're talking about potentially unlocking one of the biggest secrets of the universe just by studying these tiny particles.
It's possible. And not just dark matter. These exotic particles might help us in our quest to, like, unify the forces of nature.
You mean like finding one theory that explains gravity, electromagnetism, the strong and weak force all together?
Exactly. It's been a dream of physicists for ages. And studying gluons, the strong force, it might be a key part of solving that puzzle.
Wow. Okay, so we've gone from cosmic glue to potentially explaining dark matter and unifying the forces of the universe. My mind is officially blown. But let's step back a second. You mentioned those scientific papers. What are they telling us about all of this?
Both of them really emphasize just how complicated gluon dynamics are. They go into color confinement, asymptotic freedom, but in a much more, well, mathematical way than we've been talking about.
More for the physics PhD crowd then.
Maybe. But the cool part is how they use these complex theories to make predictions we can actually test in experiments, like at the LHC.
So how do we go from like complicated equations to real-world experiments?
Well, one paper focuses on how researchers are using lattice QCD to simulate gluons in extreme conditions. Remember that grid idea?
Yeah, the virtual universe.
Right. They're using it to study things like the properties of glue balls and how gluons behave at super high temperatures and densities, like conditions similar to the early universe or even inside neutron stars.
We're building these tiny virtual universes to see if our theories hold up.
Exactly. It's a powerful tool for making predictions about what we might see in experiments like those at the LHC.
And the other paper, more lattice QCD.
Some, but it also highlights a totally different approach: machine learning.
Machine learning again. I thought we were done with that.
I know, right? But it turns out it's incredibly useful for analyzing all the data that comes out of those LHC experiments.
Okay, how does that work? How do you use machine learning to study something as tiny as a gluon?
Think about it. When you smash protons together at the LHC, you get this huge spray of particles. Tons of data, super complex. Machine learning algorithms can sift through that, find patterns, spot anything unusual that might signal new particles or weird gluon interactions.
So it's like having a superpowered research assistant that can find a needle in a haystack of particle data.
Exactly. It helps us make sense of the chaos and maybe see things we would have missed otherwise.
So we're using giant colliders, complex simulations, and AI, all for these tiny particles. It makes you realize just how important they are. But what are we specifically looking for in these experiments? What kind of data are we trying to get, and what will it tell us?
One of the big things is evidence for those exotic particles we talked about. Glue balls, hybrids, anything unusual. We're also trying to figure out how gluons behave in extreme environments.
Okay, those are the big goals. But what about the actual nitty-gritty? What are we measuring?
The energy of those particles produced in the collisions is super important. Remember those gluon jets? We study those, the types of particles, how their energy is spread out. It tells us about the strong force itself.
Like analyzing the shrapnel from an explosion to understand the bomb that went off.
Perfect analogy. More data, better understanding, and of course, always looking for anything weird, any hint of those glue balls or other exotic particles.
The cosmic treasure hunt. And the more we dig, the more we understand about the universe.
Exactly. And that brings up a really important point. Studying gluons, it's not just about satisfying our curiosity, it has real-world implications.
Okay, you've got my attention. Tell me more.
One area where gluon research could make a real difference is in developing new materials.
Materials. How so?
Think about it. At the most basic level, materials are atoms held together by, you guessed it, the strong force, mediated by gluons. If we understand how gluons work, how they affect quarks, we might be able to create materials with totally new properties.
So we could engineer materials that are like stronger, more flexible, or maybe even have properties we haven't even thought of yet.
Exactly. Imagine materials that are lighter but stronger, more resistant to heat, maybe even superconductors. The possibilities are huge.
That's amazing. From these tiny particles to revolutionizing the materials we use every day.
It is pretty remarkable, and it's not just material science. Gluon research could also change how we understand the universe as a whole.
We talked about dark matter and the early universe. What else can gluons tell us about the big picture?
For instance, by studying gluons at really high energies, we can get a glimpse into what things were like just after the Big Bang.
We're talking about using these tiny particles to probe the very first moments of the universe.
Exactly. It's like a time machine letting us peek back billions of years. And by understanding how matter behaved back then, we can learn more about how the universe we see today came to be.
It's mind-boggling that something as small as a gluon could hold such profound secrets about the universe's history.
It is truly humbling. It just shows that sometimes the smallest things can have the biggest impact.
You know, through this whole deep dive, it feels like we're just scratching the surface when it comes to gluons. Like we've opened this door to a whole new world and we're just starting to explore it.
I totally agree. Gluon research is brimming with potential. With every new discovery, we peel back another layer of the mystery, revealing even more complexity and beauty.
So for our listeners out there, if this has sparked your curiosity, I encourage you to keep learning. There's so much out there to discover, from articles to research papers.
And who knows, maybe one of you will make the next big breakthrough in gluon research. Maybe you'll uncover a mystery we haven't even imagined yet.
The world of gluons is truly fascinating, full of wonder, complexity, and the potential to change how we understand the universe.
And as we continue to explore, one thing's for sure, there are incredible discoveries waiting to be made.
Until next time, keep those minds curious and keep those questions coming. There's a whole universe out there to explore.
You're absolutely right. There's so much we still don't know about gluons. It's exciting.
So where do we go from here? What are some of the big mysteries scientists are trying to crack?
Well, one really interesting area is the search for what we call exotic particles. We talked about glue balls, but there could be even weirder stuff out there.
Weirder than particles made entirely of glue. Okay, I'm listening.
Think about it. We've got these basic pieces, quarks and gluons. They interact through the strong force. We know they make protons, neutrons, maybe glue balls, but what other combos are possible? Maybe there are particles we haven't even imagined yet. Like one idea is hybrids, particles made of both quarks and gluons stuck together.
So it's not enough to understand gluons by themselves. We need to figure out all the ways they can combine and maybe create whole new forms of matter.
Exactly. It's like imagine you've got a Lego set. You can follow the instructions, build what's on the box, but then you can also get creative, right? Combine those bricks in new ways, build something totally unique.
That's like a cosmic Lego set, building blocks of the universe. Okay, so let's say we find these exotic gluon particles. What could they tell us? Could they revolutionize physics?
It's hard to know for sure, but they could give us clues to some of the biggest puzzles in physics.
Can you give me an example?
Well, there's dark matter.
You mean that invisible stuff that makes up most of the universe?
That's the one. We know it's out there, but what is it? Some theories say it could be particles interacting through forces like the strong force, maybe involving gluons or these exotic gluon particles.
So by studying these tiny particles, we might actually unlock the secrets of dark matter.
It's a possibility. And it's not just dark matter. These exotic particles could even help us in this, grand quest to unify the forces of nature.
Unify the forces, you mean find one theory that explains everything, gravity, electromagnetism, the strong and weak forces, all in one neat package.
Precisely. It's been a dream of physicists for, forever. And studying gluons, the strong force, could be a big step towards that.
Wow, we've gone from cosmic glue to potentially explaining dark matter and unifying the forces of the universe. My head is spinning. But okay, let's bring it back down to earth for a minute. You mentioned those scientific papers. What are they telling us about all of this?
Well, both of them really highlight how complex Gluon dynamics are. They go deep into things like color confinement, asymptotic freedom, but in a more mathematical way than we've been talking about.
So, more for the physics experts then.
Maybe, but what's cool is they use these theories to actually make predictions that we can test in experiments, like at the LHC.
Okay, so how do we go from like equations on a chalkboard to real-world experiments?
Well, one of the papers focuses on how researchers are using lattice QCD to simulate gluons under extreme conditions. Remember that grid idea?
Yeah, like building a virtual universe.
Exactly. They use this technique to study things like the properties of glue balls, how gluons act at crazy high temperatures and densities, like conditions similar to those in the early universe or even inside neutron stars.
So we're building tiny virtual universes to test out our theories.
You got it. It's a really powerful way to make predictions about what we might see in experiments, like those at the LHC.
What about the other paper? Is it also about lattice QCD?
It touches on that, but it also highlights a completely different approach, using machine learning to study gluons.
Wait, machine learning again? I thought we were done with that.
It seems strange, I know, but it's actually super helpful for analyzing all that data that comes from the LHC experiments.
Okay, but how does that work? How do you use machine learning, which is used for things like recommending movies, to study something as tiny as a gluon?
Think about it this way. When we smash those protons together at the LHC, we get this enormous explosion of particles. It creates a huge amount of data, and it's very complicated to analyze. Machine learning algorithms can sift through all of that, look for patterns, and spot anything unusual, like signs of new particles or strange gluon interactions.
So it's like having a super smart research assistant that can find a needle in a haystack of particle data.
You got it. It helps us make sense of the chaos and maybe even see things we would have missed otherwise.
It's amazing that we're using giant colliders, complex simulations, and now even AI. All of that to understand these tiny particles really shows how important they are. So what exactly are we looking for in these experiments? What kind of data and what will it tell us?
One of the main things is evidence for those exotic particles we talked about, glue balls, hybrids, anything out of the ordinary. We're also trying to really understand how gluons behave in extreme conditions, like those found in the early universe.
Okay, those are the big goals.
Mhm.
But what about the actual details? What kind of measurements are we making?
Well, one of the most important things we study is the energy of the particles that are produced in the collisions. Remember those gluon jets? We look at the types of particles in those jets, how their energy is distributed. That tells us a lot about the strong force itself.
So it's like we're analyzing the debris from an explosion to figure out what kind of bomb went off.
That's a great analogy. And the more data we collect, the more we understand about the strong force. And of course, we're always on the lookout for anything unusual, any sign of those glue balls or other exotic particles.
It's like a treasure hunt on a cosmic scale. And the more we dig, the more we learn about the universe and how it all works.
That's a great way to put it. And this leads to a really important point. Studying gluons, it's not just about satisfying our scientific curiosity, it has real world implications, things that could potentially impact all of our lives.
Now you've got my attention. Tell me more.
One area where gluon research could really make a difference is in material science.
Materials. Really? How
So,
so?
well, think about it. At the most basic level, materials are just, atoms stuck together by the strong force. And gluons, they're the messengers of that force.
Right, right. So if we can figure out how gluons work, how they influence those quarks.
We might be able to design materials with, completely new properties.
So we're talking stronger materials, more flexible, maybe even stuff we haven't even thought of yet.
Exactly. Imagine materials that are lighter but way stronger, more resistant to heat, pressure, maybe even superconductors. There's a whole world of possibilities.
Wow, that's pretty incredible, from these tiny particles to like revolutionizing the way we build things.
It is. And it's not just materials. Gluon research could change how we understand the entire universe, too.
We talked about dark matter and the early universe. What else can gluons tell us about the big picture?
Well, one thing is, by studying gluons at these super high energies, we can get a glimpse into what things were like right after the Big Bang.
So we're talking about using these tiny particles to like look back in time billions of years.
Exactly. It's like a time machine. Helps us understand how the universe evolved to become what it is today.
It's mind-blowing to think something so small could unlock such huge secrets about the universe's history.
It really is. It just goes to show that even the tiniest things can have a massive impact.
Through this whole deep dive, I keep getting this feeling that we're just scratching the surface with gluons. It's like we've opened this door to this amazing new world, and we're just starting to peek inside.
I couldn't agree more. Gluon research is so full of potential. Every new discovery just peels back another layer, reveals even more complexity and beauty.
So for our listeners, if you're intrigued, keep exploring. There's a ton of information out there, from like basic articles to those really in-depth research papers.
And who knows, maybe one of you listening will be the one to make the next big gluon discovery. Maybe you'll uncover a mystery we haven't even thought of yet.
That's what I love about science. There's always more to learn, always more to discover. The world of gluons is truly fascinating, full of like wonder, complexity, and the potential to reshape our understanding of the universe. Thanks for joining us on this deep dive, everyone.
Until next time, keep those minds curious and keep asking questions.